Welcome to the video key for quiz 6. All right, number 1, we have a reaction that's at equilibrium and we're going to add some water. So looks like this is Le Chatelier's principal problem. We're looking at how if we perturb an existing equilibrium, what happens. So the correct tool to use is Q, so let's go straight to Q for this reaction. So we've got concentration of acid, of hydrogen ion, concentration of formate ion, and we have formic acid itself. Okay, so all those are aqueous, so they all go into Q. And it's asking us for the ratio of formic acid to formate. So it's asking what happens to this ratio? What happens to the ratio of acid to its corresponding anion? Okay, what happens to that ratio? So we could call this, just call it ratio. Okay, so what happens to that? So, well, what happens to Q when we add this? When we add this, we know what's going to happen is, at first the ratio will be unaffected, right? Because if we double the amount of water, then both of these concentrations are going to go down by a factor of 2. Okay, but let's look at the effect on Q. Hydrogen ion concentration is going to go down, formate's going to go down, formic acid's going to go down. So notice they're all going to go down in proportion to the amount that the volume changes, but there's 2 factors of dilution on top, right? So both of those are going to get smaller. So Q after dilution, it's going to be a smaller number than Q before the dilution. So Q got smaller. So that means that since Q got smaller, K equilibrium is going to be greater than the Q after the dilution. And we know that when K is greater than Q, the reaction has to react to the right. We're going to make more products. If we're going to make more products, we're subtracting from acid. So this is going down, but we're actually going to be making some of the formate ion. So the ratio of acid to anion is going to get smaller. Okay, so the ratio of formic acid to formate is going to get smaller. We're going to make more of the anion. We're making more products and less reactants. So we're going to say it decreases. Which acid is weaker? So if we look at acids, and I'll just abbreviate for weak acids HA, it's just the same as the equilibrium we just did, right? So we have some propensity to break up to form hydrogen ion and some anion, but most of the molecules are still in their intact state, right? We don't dissociate all the way. We just dissociate some fraction of the molecules. So the Ka is just the equilibrium constant for this. And so the pKa, any kind of P, whether it's pH or pKa, is going to be the negative base 10 logarithm of the thing. And so in this case, it's the negative base 10 logarithm of the Ka. So if we think about a stronger acid, Ka for the stronger weak acid, so we're still talking, all these are going to be weak acids, right? But for a stronger weak acid, it's going to have a bigger Ka than for a weaker weak acid. Okay, so when we're comparing 2 weak acids, the one that's stronger of the 2 is going to be the one with the bigger Ka. So if you plug a bigger number into K, that's going to make the logarithm bigger. And in contrast that, if you put a smaller number into K, that's going to make the logarithm smaller. And notice we're putting a negative here. So what that means is if we put a weaker K, a smaller K into this equation, that's going to make the pKa a bigger positive number. So pKa for the weaker is going to be a bigger number than pKa for the stronger. Now we're still just talking about weak acids, but we're saying comparatively stronger and weaker. The pKa is a bigger number for the weaker of the 2. And it's because this is a negative logarithm, not just a logarithm, right? So for weak acids, Ka's are going to be less than 1. So if we have a really weak one, the Ka is going to be a really, really small number, maybe like 10⁻8 or something. So if we plug in a really, really small number, the logarithm is going to be a big negative number. And if we take the negative of that, it's going to be a big positive number. So the smaller the Ka, the bigger the pKa. All right, we wish to protect a plate made from copper from corrosion, so we need a sacrificial anode. So this is the idea that we have something we care about, some fabricated piece that is serving maybe a structural purpose, and we're going to maybe it's in the environment, maybe it's even outdoors. If we connect it with a wire to an active metal, something like something more active than copper, like iron, then the iron can start corroding and forming ions because it's more active. It's got a less positive reduction potential than copper. Well, if it's doing that, it's going to start producing electrons, and those are going to flow through this wire. And we're putting electrons on here. So the minute, if you imagine starting to form a copper ion, as soon as you start to form a copper ion, you're going to be pushing electrons back onto it and making it a metal. So by putting all these electrons on here, we're preventing the copper from being oxidized. That's how sacrificial anodes work. Well, to do this, we have to have a metal that is more active than copper. So to see which answer is right, we've got to use reduction potentials. So let's go look at a table of reduction potentials. Okay, so we can find our equation sheets under course materials. So we'll go to course materials and click on the latest version of the equation sheet and look and see what we can find. Okay, so looking at this, we can see that we were trying to protect copper. So here's our copper, right? We have metallic copper. Oh, that's the wrong one actually. Copper. Here we go. Metallic copper. And we're trying to make sure that it does not get oxidized, right? So copper has a reduction potential of 0.34 volts. So anything that is more noble than copper, something like silver, you could build a voltaic cell where the silver is the cathode and the copper is the anode. That means the copper is corroding. That's exactly what you don't want. So if you connect any metal that's more electropositive than copper, you're going to actually corrode it. Okay. Notice this iron thing doesn't matter here because we're not talking about this. These are ions, right? We're not building a sacrificial anode out of iron metal, so we disregard the iron here. But silver certainly would not work. Gold is way up here, so if you attach gold to copper, the copper would corrode and the gold would be the cathode, which is not what you want. So silver and gold are both noble metals. Let's go back and look at what other metals are here. So silver and gold are bad choices. Let's just go ahead and cross those off. Okay. What about iron, tin, and chromium? Let's go look at those. Okay, so let's go look for metallic iron. Where is that? Over here. Okay, so we can see there's a potential where we could corrode iron to make iron 3, and that's more negative than copper, so that would work. We've got iron to corroding to form iron 2. That's more negative than that. So we can definitely corrode iron and in the process protect the copper, so copper would work. What about tin? Okay, we can notice we can corrode tin. It's got a more negative reduction potential than copper. And the last one is chromium, and we can see that's actually quite negative. So chromium would also protect our copper. So any of the ones that are below, that are more negative in reduction potential than our copper, which was here. And notice there's two different reactions for copper. We could form copper 1, or we could form copper 2. And notice that we're well below either one of those. Okay, so if we hook up copper and either tin, chromium, or iron, because this is a more positive reduction potential, it's going to be the cathode. So the copper is going to not corrode. So getting back to this, we can say that we could use any one of these as a sacrificial anode in contact with copper. Okay, increasing charge density has a systematic effect on one or more of these parameters. Which ones? So looking at this, we saw the high charge density. So let's just define charge density as charge over ion size. And we saw that these salts are less soluble when we did the experiment. If a lot of the salts that were insoluble had high charge density, and a lot of salts that were more soluble had low charge density. So high charge density meant low solubility. Well, low solubility is the same as saying delta G for forming a solution in water. The delta G here is going to be unfavorable, so it's going to be more positive. Okay, so the less soluble you are, their way of saying this is your KSP, your equilibrium constant for forming a soluble salt, is going to be less negative, right? The less soluble you are. Okay, so there's definitely a trend here. Well, these trends must be driven by either entropy or enthalpy. So let's write this out. So we could say one of these is going to be driving the trend in delta G standard. Oops, these are all solubility. Okay, so this is all taking a salt in the solid phase and dissolving it in water to make salt in the aqueous phase, to separated ions there. So which one is it? Well, when you break a salt apart, that costs energy, and the bigger the charge density, the more energy cost is. And when that salt interacts with water, that releases energy, and the more charge density, the bigger that effect is. So there's no net effect here. But if we looked at delta S of solution, when you break apart a salt, you create a bunch of entropy. Your delta S is positive for the salt being blown apart into ions, because you can imagine taking ions in the gas phase as sort of like you could do this as, conceptually you can break this into two steps, right? Break the salt into ions, that's the lattice process, and then take those ions and hydrate them. So delta S for this first step is going to be positive regardless of hydration enthalpy, not really affected by hydration, not affected by charge density, okay? Just by virtue of forming a gas phase, you're making all this entropy. The second step here, you're going to be decreasing entropy because, first of all, the ions don't move as much when they're in the water as they do in the gas phase, but more importantly, we're orienting water molecules around each of the ions. And that orientation effect is strongly driven by charge density. So the bigger the charge density, if we increase the charge density, if we make that number bigger, delta S is going to get either less positive or switch from positive to negative or get more negative. So there's a strong trend between charge density and the delta S of solution. Okay. So bottom line, high charge density ions tend to orient water molecules more than low density ions, and that means that the delta S of solution is worse than it would be otherwise as you increase charge density. And because the delta S is worse, the delta G is also worse. Okay, the next few questions deal with this Gibbs energy versus reaction progress graph. So we've got reactants over here, so reactants. We got products over here. And as we imagine going from pure reactants to pure products, we're going from left to right. Okay, and we've got this filled circle here. I'm going to erase this because I only want to have one filled circle on there. So maybe I'll put unfilled circles at the start here. Unfilled circle. Okay, so if we look at this graph, we know that we can take the difference between products and reactants, and we can say we delta'd the Gibbs energy of final minus initial, we get a positive number, right? Okay, we can see that on the graph. We can also see that the slope here is a positive number, and here's a negative number. And we know that the system's going to go I'm going to erase this because, yes, it's a positive slope, but we know what's going to happen. The system trends towards the minimum of Gibbs energy. So if we're over here, we're going to go down, which means the reaction is going to go forward. If we're here, we're going to go down, which means the reaction is going to go backward. So another way of saying this is that we can draw a little line dividing this and saying over here on the left-hand side, delta G for the forward reaction is negative, and over here, delta G for the forward reaction is positive, right? It's not spontaneous to go forward, it's spontaneous to go backward. And then we could draw a little arrow right at the bottom and say it must be that delta G is equal to 0 here because the forward or the backward is not spontaneous. Okay, so I think that's enough annotating there. So it says the current state of the system is given by this filled circle. Okay, so what's in the beaker right at this moment, that's the filled circle there. Okay, what's the size of delta G standard? And notice delta G standard is about the reaction. It's not about where you're at any specific moment in time. So it doesn't care what's in the beaker. It's just saying if I take pure products minus pure reactants, I get that that's a positive number. So delta G standard is a positive number. The products have more Gibbs energy in them than the reactants. Size of delta G. Well, delta G, now we actually do care where we're at, and where we're at is, and we'll just draw a little annotation here that we're talking about there, that's the current state of the system. We can see that the slope is down and to the right, which means delta G is negative. Forward reaction spontaneous. What's the size of K? And we can do a couple of things here. One thing to do is we could say that delta G standard is equal to negative RT log of K equilibrium, and we said delta G standard is a positive number. So the only way to get a positive number is if this whole thing here is negative, right? Because then a negative times a negative will give you a positive. So it must be that that's a positive number, negative number, and the only way to get a negative number is if K is going to be less than 1. So if K is less than 1, we plug it into a logarithm, we get a negative number, negative times a negative gives a positive. Okay, so we know K has to be less than 1. We can also just see that from the graph. If we look at this graph here, we can see that we're way over on the left, right? And this is equilibrium here, and we can see that equilibrium is on the left-hand side of the graph. So clearly that means that at equilibrium we're going to have more reactants than products. K is less than 1. All right, what about the size of Q? Looking at this, Q is where we're at on the x-axis, which is this filled circle. And we can see, if we look at that filled circle, that the value of Q is less than K, right? We can see that K, I'll just draw a little arrow here, K is that the value of the x-axis at that minimum, right? It's what your ratio of products to reactants will be at equilibrium. And we can see that Q is clearly less than that. Q is that filled dot representing the current state of the system, not the equilibrium state. So Q is less than K. And since K was less than 1, we can see, oh, okay, if K is less than 1 and Q is less than K, then Q has to be less than 1 as well. How do they compare? Oh, we actually already said that Q was less than K. So another way of saying that is K is greater than Q, so we expect to react in the forward direction from that filled circle. Okay, classify the current state of the reaction mixture. And we already said that the forward reaction is spontaneous, so let's go ahead and circle that, right? Because K is greater than Q, or delta G is negative, or the slope's negative. So all of those things tell us that we're going to react in the forward direction. Okay. Corrosion lab attacked a piece of zinc to a steel nail. After a few minutes, you notice red color around the nail. No blue color was present. Use this information to answer the questions below. And there is a picture, so we can annotate it a little bit by having some sort of red color appear around the nail just to match our description. Okay, and we have to figure out what this means. Okay, so you have a wire connecting your zinc. So we'll just label this as being zinc. Okay, and then we've got an iron nail, so we'll just put an annotation on here that that's iron. And the question also asks us about the flow of sodium ions and chloride ions. So we have sodium and chloride in here when we cast our gel. So they're going to go in a certain direction. So we'll just write those in now. Okay, so let's shrink this down a little bit so we can see our questions a little better. Okay, so label the cathode and the anode. All right, so we have to say, we have some clues here. There's red around the nail. There's red around the nail. So what does that mean? So we may remember that red in our experiment meant that oxygen was being reduced. And we put phenolphthalein in because we know that phenolphthalein reacts with bases to form a pink color or a red color. So it must be that we have a reaction that produces hydroxide ions. And remember we said that red is oxygen being reduced. So we want oxygen being reduced and we want hydroxide being produced as well. And if we look at this reaction, we can see oxygen is being reduced and it's producing hydroxide. So that looks like our reaction that's producing a red. So we can write that we've got oxygen and 2 waters, 4 electrons being reduced. So let's go ahead and write that as our cathode reaction. Okay, so we've got 4 oxygen atoms, we've got 4 hydrogen atoms, and if we look at the left-hand side and right-hand side, they both are -4, so it looks like that half reaction is balanced. And this is going to react with the phenolphthalein to make our red color. What about the anode? Well, iron can't be being oxidized. I mean, something has to be oxidized, but iron can't be because remember, the notes here said there was no blue, and we had a dye that would react. It was colorless, but it formed Prussian blue, a bright blue compound, when iron 2 was present. So it must not be the iron that's being oxidized. So we know something else is being oxidized. We know zinc is easily oxidized. So we're going to write the zinc reaction. And we could also look on the equation sheet, but we see zinc can lose 2 electrons to form zinc 2. Okay, so we look at that, we say, okay, we're gonna posit that reaction. Now, if zinc is producing those electrons, they have to go somewhere, right? So we're gonna make some zinc ions, but it's leaving behind 2 electrons, and so we're gonna end up putting all these negative charges on here. They have to go somewhere. And so this is gonna give a buildup of negative charge, and that's going to repel the electrons through the wire. Okay, and that's good because we need electrons for the oxygen reaction, right? They're being consumed, so we've got those going over there. Okay, so far so good. We should label the cathode and the anode. So since oxygen's being reduced around the nail, that's going to be our cathode. And we should label this not just on some sort of general side, it's the actual object there that's conductive that we're going to call our cathode. And oxidation's occurring at the surface here, so this is our anode. So we've got those. Show the flow of electrons we already did. Now what about the flow of ions? Well, one easy way is to remember, look, we've got this loop of negative charge, right? It looks like negative charge is moving in that in sort of a, in this case, it's a counterclockwise loop. So we've got to have these just continue that loop, right? Because chlorides are negative just like electrons are negative. So the sodium is going to move in the opposite direction. Now let's do a plausibility check and see if that makes sense. Well, on the zinc side, notice we're forming zinc ions. We're adding positive ions. We got to balance that somehow. And having the chloride ions move in this direction helps to balance those zinc ions. On the other side, if we look at our iron, we are, if we look at our half reaction here, we have hydroxide being produced. So we're having hydroxide being produced here. So we have to somehow balance those negative charges, and so our sodiums are moving in this direction. Okay, so we've got our flow of ions. Oops, where is that? Yeah, our flow of ions, we can mark that off. Oh yeah, we already said that the anode is negative, so let's put a little plus sign here on our cathode. Okay, and this makes sense too. If you look at this, remember that this is a voltaic cell, so the flow of electrons has to be driven by the chemistry. And so the chemistry is piling up electrons on the anode over here, building up a negative charge, and so they naturally flow away from that negative charge to the positive charge on the cathode. All right, I think that is it for that question. Okay, so notice the geometry is different from having two different beakers, but all the principles are the same. So be able to analyze any cell like this regardless of the geometry, even if it looks sort of different from what you're used to. Okay, balance this equation in acid. This one had some pretty big coefficients, and depending on the choices you made, they could have been really big because there was this typo in here. So this is why this question, basically 4 points of it was extra credit and the other 4 was the original credit. So your scores on this question, instead of ranging from 0 to -8, they range from -4 to +4. Okay, let's go ahead and balance this. We start by splitting into half reactions, and you want the main atoms, that is the atoms being oxidized or reduced, to be the same number. So we can either have this, some of you chose to have 3 permanganates and 3 manganese, and that's fine too. This is basically you get the same answer I did, but multiplied by 3. Let's split up our methanol being oxidized up to this compound, and there's nothing else to say about that. Okay, so let's go ahead, sort of put a little barrier here between our 2 reactions, just to say like we're going to keep them separate, our 2 half reactions. All right, start by balancing oxygen. So I'm going to put 4 waters over here. Then I got to balance my hydrogens, so I'm going to put 8 H plus over here. And now if we look at our charges, I've got 8 minus 1, that's going to be a +7, going to +2. So it's a difference of 5. I need to somehow balance that since I have +7 over here. If I add 5 electrons, that'll do the trick. So looking at this, you can also check oxidation numbers. This isn't necessary, but it's a good check. If you do your oxidation numbers, you see that this is +7 and this is +2, and the difference between 7 and 2 is 5. So we got that part right. That's just like a little internal check you can do. All right, checking out this side, I need to balance my oxygens because I have 2 on the left, 2 on the right, and 1 on the left. So I'll add a water over here. Okay, so I've got 2 hydrogens here and 4 here. That's 6. I only have 2 here, so I need 4 hydrogens. And now I check the charge. I'm neutral on the right, neutral on the left, but on the right I have 4, so +4. So I need to make it neutral on both sides, so I'll add 4 electrons. If we do the oxidation state of carbon here, if you do your oxidation numbers, you'll see that this one is -2. If you do your oxidation numbers over here, you'll see this one's +2. So it looks like carbon lost 4 electrons, and that's what we have. So we're good. Our internal check worked out. So doing this, we're like, oh no, we have 4 here and 5 here. So we're going to have to do a common denominator. So we're going to, if we think about it, we really can't get one at 10. We're going to have to go all the way up at 20. So we're going to have to multiply this by 5 and this by 4. So then we'll write the final thing out, put them together. So we multiply by 4, we get 32 hydrogen ions plus 4 permanganates. And then we see on the reactant side, let's go ahead and finish the product side. So we multiply by 4. So we've got 4 times the manganese ions, and 4 times 4 for the water, so 16 waters. And now we can do this other reaction over here, so we've got to multiply everything by 5. So we've got 5 of the methanols, five waters, and on the right hand side we've got 5 of the oxidized compound. I guess it's an aldehyde, so that's CH2O2, and 5 times 4 is 20 hydrogen ions. And okay, so we should be balanced, but let's go ahead and cancel some stuff here. So we've got 5 waters on this side, so let's subtract 5 from there and subtract 5 from here and say 11 waters. And we've got hydrogen ion on both sides too. We've got 20 on the right. We have there was a mistake. Yes, we multiplied. Oh, I see, I just miswrote this. We multiplied 4 times 8, so this should be 32. So let's fix that 32. Oops. Okay, there we go. So yeah, 4 times 8 would give us 32 of those. So we've got 32 hydrogen ions here, and we have 20 here. So we can subtract 20 from this side, subtract 20 from here. That's going to give us 12 hydrogen ions. All right, so our final, I'm just going to circle the pieces that are left. And we'll circle the pieces that are left over here. And we'll check to see if it's balanced. So hydrogen, well, let's just do oxygen first. Now let's do manganese. Okay, I got 4 manganese atoms and 4 manganese atoms. Good. We've got 5 carbons and 5 carbons. Good. Now we'll do oxygen. So oxygen, we've got 4 times 4 is 16. And then we've got 5. So that is 16 plus 5, or 21. On the other side, we've got 11 waters, so that's 11 oxygens, plus we have 5 times 2 over here, so that's 10. So 11 plus 10 is 21. Okay. Hydrogens, let's check those. We've got 4 for each methanol, and there's 5 of those, so that comes out to 20, plus the hydrogen ions here, so that's 32. We go to the right-hand side, we've got 2 for every water times 11 is 22. And then we have 2 for this oxidized compound. For each one, there's 5. So 5 times 2 is 10, plus our 22 is 32. Good. And charge. On the left-hand side, we've got a negative 4, and we've got a positive 12, so that's plus 8. And we look at the right-hand side, and we've got 4 manganese, each one's plus 2, so that's plus 8, and that's it for the charge. So we're done. So we can see that since the charge balances and the atoms balance, this is H+, it should just say H, because we're just counting atoms at this point. So we know for sure that it is balanced. Some of you multiplied it, as I said, you multiplied it by 3 because you wanted to preserve that rather than preserving the 1 over here, and that's totally fine. You just multiply all of my coefficients by 3 and you get the same answer. Number 13, we have an equilibrium constant at a specific temperature, so you could say we have K at T1. We also have delta H for the reaction. And we want to find K at some new temperature. So we're going to raise the temperature, right? So you want to find K at T2. All right, so the tool we need is the Van Hoff equation. So we've got the log of an equilibrium constant is a function of the heat of reaction and the entropy of that reaction. And this is useful if we want to do a graph. We could graph a bunch of equilibrium constants, the log of a bunch of equilibrium constants, as a function of 1 over t, as you did in your lab, and then we know this is going to be the slope, and this part here is going to be our y-intercept. So we get y equals mx plus b. We only have 2 points though, right? We have our original temperature and our original equilibrium constant, and we want to go to a new equilibrium constant and a new temperature. So when you've just got 2, you want to transform this graphing form into a 2-point form, and you can do that by just writing it twice. So you write log of k at t2 is equal to negative delta h of reaction 1 over t2, and then we write it again at some other temperature. In this case, we'll write it at the reference temperature T1. These are multiplies there. And you can add a reaction to another reaction, or equation to another equation, and you can subtract. So we're going to subtract this whole equation from the equation above. And we do that, we can see, in this course we're assuming that delta H's and delta S's are approximately constant with temperature, which means these are the same. So we can just cross out, they're going to cancel. So then we have the log of k at t2 and k at t1. And when we subtract logarithms, that ends up being the log of a ratio. So log of k of t2 over k at t1. And we can pull out the delta h over r and just have 1 over t2 minus 1 over t1. Okay, so all we've done is subtract the same equation, but we've just written it under 2 conditions. Okay, so what changes is t and the resulting k. So if we look at this, the only unknown is k at t2. So we can solve that with a little bit of algebra. So let's not put that there. Let's okay, so we'll put this down here. So let's solve for k2. So we're going to take the exponential of both sides. So we've got k of t2 over k of t1 is equal to the exponential of this whole thing here. Okay, and then we'll just multiply k at t1 to both sides. So k at t2 is equal to our original k times this exponential. Okay, so common mistakes to watch out for. Number 1, you got to use kelvins here because r is going to be has reciprocal kelvins in it. Number 2, don't do this. Okay, do not do this. 1 over t2 minus 1 over t1 is not equal to 1 over t2 minus t1. So even if you wouldn't do that algebraically, you might accidentally do it in your calculator. So watch out. This causes a lot of problems for students. So don't do this. Other problems: not converting from kilojoules to joules in your delta H because your R is going to be in joules, or using the wrong R, right? And that'll happen if you don't check your units. So we're going to plug in all our units here. So going back up in the problem, we see our original K was 3.610 negative 7. And we're going to multiply that by this exponential. So we take our heat of reaction, which was a positive 104 kilojoules per mole. So we got negative a positive 104 kilojoules per mole divided by R, 8.314 joules per mole per Kelvin. And how do we know that it's this R? Because we're going to need to cancel the units. And we can check later just to make absolutely sure we're right about that. And we're going to 410 Kelvin. We started off at 298. Oh, the other pitfall that can happen is make sure that you pair up the right K with the right T. Like these have to be in order. You're gonna get either a sign error or it's gonna change in the wrong direction. Okay, so one thing that will help is to make a prediction at the start. We have a reaction that is endothermic, right? It absorbs heat. So if we raise the temperature, we expect K to get bigger. So if it doesn't get bigger, we know we made a sign error somewhere. Okay, so let's go ahead and plug all this in. So if we take this exponential, we're going to end up, oh, actually, let's check our units first. So joules cancel joules, mole cancel moles, reciprocal kelvins on the bottom, cancel reciprocal kelvins on the top. So it's unitless, which it had better be because we're plugging it into an exponential. So we get that the exponential part of it came out to be 9.54 times 10 to the 9.55 times 10 to the fourth. So if we multiply that by 3.6, 10 to the negative 7, we get 3.44 times 10 to the negative 2. If we wanted to, we could just write that as 0.0344. So that's our new version for K at our new higher temperature. And notice it is a much larger number, which is what we predicted at the start. All right, that's it for the key for quiz 6. Thank you for watching.